We're lucky to have the Blue Mountains to the east of Walla Walla, and I'm headed up there today to talk a little bit about the story of Chapter 5. Okay, folks, I'm up here on McKay Grade, which is up in the hills east of Walla Walla, and the story of Chapter 5 is not topography. Arguably, it could be fluid flow. It's a very windy day today, but it's not going to be fluid flow either. Chapter 5 is about multiple integration, and that's a tool essentially. And one of the big applications of multiple integration is not topography, but rather what's underneath the topography. Have you ever thought about the question of how do people know what's inside the Earth? The Earth is roughly 6,000 kilometers in radius, and the deepest hole that any human has ever dug is about 12 kilometers. So we've barely scratched the surface. How do we know what's deeper? How do we know what's down at 2,000 kilometers, what's down at 4,000 kilometers below the surface of the Earth? There are a lot of techniques that people have used to infer what the structure of the inside of the Earth looks like, and multiple integration definitely plays a role in that, as do lots of other kinds of mathematics. So I'm going to walk you through that from a very non-expert point of view. I'm not a geologist, I'm a mathematician, but I can talk about some of the mathematical techniques that have been brought to bear to help us understand the inside of the Earth. Okay, one application of multiple integration that's outside really of topography or fluid flow is how it might be used to study the interior of the Earth. We kind of live up here on the surface of the Earth, and even the deepest holes that we've ever dug only go about 12 kilometers into the crust. And this isn't really to scale here, as we note here. Maybe we're kind of a little dot is the deepest hole that we can imagine that we've ever kind of come up with here. And yet we know with some amount of certainty that there's a solid inner core made up mostly of iron, a liquid outer core, this mantle, which is a mix of stuff from the inside and crust, and then various levels of sort of mixing of crust. And it comes in these layers. And how do we know that if the deepest hole we've ever dug is 12 kilometers? There are a couple of ways that we know this. Let me just kind of zoom in here. Here's a different diagram. Where we've got the crust, the upper mantle, transition zone, which is mostly oxygen, silicon, magnesium, and iron. And then we've got lower mantle, oxygen, silicon, magnesium, and iron. And then down in the outer core, we have iron and nickel. And in the inner core, iron and nickel. Iron and nickel happen to occur a lot, iron in particular. Iron is sort of at the bottom of the atomic table. You don't get any energy out of breaking it apart, and you don't get any energy out of fusing it with other atoms. And so it just kind of sits there at the bottom. Iron rarely gets transmuted into anything else. Higher elements like uranium, when they split, they release energy. They're unstable. They have short half-lives, and so they tend to split into two atoms that have a lower atomic number and therefore sort of lower on the atomic table. Where does that process essentially want to end? It sort of ends at iron. Sort of at the bottom. And then at the other end, the light end of the periodic table, hydrogen, for example, we can fuse hydrogen together to get helium. We can fuse helium together to get higher elements. And that's exactly what happens inside the sun. We have fusion happening, and energy is gained when you take two hydrogen atoms and smush them together. But you don't gain any energy by taking two iron atoms and smushing them together. There's nothing to be gained there. So iron atoms neither fuse nor what's the fission. They don't do fission either. So we have a lot of iron in the world, and it sort of settles down into the middle of rocky planets like ours. Okay, how do we know what's inside? There are a couple of different approaches, and they all get glued together to kind of paint this massive picture. Um, One is mapping the Earth's gravity. So we can get a sense of what's beneath the Earth's surface by studying the force of gravity on the surface. And you might think, oh, the force of gravity on the Earth's surface, 9.8 meters per second squared everywhere, right? Well, actually, no. And here's a nice little picture of the variations of the Earth's gravity. We see it tends to be high along mountain ranges and it tends to be low in oceanic trenches. But that's not always the case, and a lot of the variation has to do with internal structures of the Earth. So that's one way. Another really interesting way is using seismic waves to understand the Earth's interior. So what happens in seismic waves, and let me go back to the diagram here. Let's say there's an earthquake that happens right here, big earthquake. What happens in that situation is you get um, waves, sort of waves of motion going through the earth. And every time a wave hits one of these layers, it reflects. And when it goes to this deeper layer, so it kind of comes off this way, and then maybe it goes down and there's even other reflections, and all the way down here maybe other reflections like this. And we can measure those. So not only do we measure kind of the direct waves, but we can measure these reflected waves off of these various strata inside the Earth. So earthquakes provide a natural experiment for us to explore the center of the Earth. And reconstructing the center of the Earth based on scattered waves is a very important area of mathematics called inverse scattering theory. Inverse scattering theory is the foundation for medical imaging, for example. Medical imaging, you send electromagnetic waves into the human body and they scatter off of the human body. They scatter off of bones in ways that are different from scattering off of organs, and you're able to reconstruct the interior. Similarly, uh, magnetic resonance, same thing. You're seeing magnetic waves, and those magnetic waves are scattered off of different parts of the body in different ways, and you're able to reconstruct the interior of the body. That's exactly how the interior of the Earth is reconstructed based on earthquakes. Now, what does this have to do with multiple integration? At every step of the way, when you're doing multiple integration, when you're doing inverse scattering theory on an object like the Earth, you're doing triple integrals. You're doing density integrals, you're using spherical coordinates and change of variable to construct these scattering models. And none of that is possible without a clear understanding of multiple integration, which is what we're going to study in Chapter 5, and right at the end, the change of variables theorem. So that's my pitch for why you should care about Chapter 5, the story of Chapter 5.